Hello everyone, let's analyze. So in the last lecture we learned what a continuous function was and how it relates to the idea of limits if you're testing for continuity at an accumulation point. So today we're going to extend some of that and learn about the arithmetic of continuous functions. What happens when you add, multiply, or divide two functions that are continuous. So suppose f and g are both continuous with the same domain at a particular point x naught. Well, then the sum of the functions is continuous, the product of the two functions is continuous, and the quotient of the two functions is continuous so long as the denominator function is not 0 at the point that you're testing for continuity. And by now, of course, we have so much machinery to choose from. Hopefully you realize that proving something like this is fairly straightforward. And we can break it into two cases, whether x naught is an accumulation point of D or not. And the reason we're going to test that is because we have so many tools with which to use that we don't have to prove 1, 2, and 3 by using a standard epsilon delta proof. We can use the tools that we have. So let's go through the two cases. Case 1, suppose x naught is not an accumulation point. Well, then the result follows simply from the fact that the sum, product, and quotient of f and g at x naught are defined, which is all that's needed to prove continuity at a non-accumulation point. In fact, you proved this in your homework, so you know very well that that's true. Now let's look at case 2. If x naught is an accumulation point, then we know from last week's theorem, you remember the one. Remember that if x naught is an accumulation point of the domain, then f being continuous at x naught is the same as the limit of f being defined at x naught and the limit being f of x naught. So now we know that f is continuous is the same as f of x naught being the limit of f at x naught. We can use that and the arithmetic of limits to put together a fairly straightforward proof. Well, let's go back to where we were. So if x naught is an accumulation point, then we know that the limit as x approaches x naught of f of x is f of x naught, and the limit as x approaches x naught of g of x is g of x naught. Therefore, the limit as x approaches x naught of f plus g is the limit as x approaches x naught of f plus the same limit of g, which is f of x naught plus g of x naught, which is the function f plus g evaluated at x naught. So in fact, because this is true, we know from previous week's theorem that the limit of f plus g at x naught exists and is equal to the evaluation at x naught. Therefore, it's continuous at that point. Similarly, from our arithmetic of limits, we can distribute the limit across the product. The limit of f times g is the limit of f times the limit of g, which is f of x naught times g of x naught, which is exactly the product function fg evaluated at x naught. And again, so long as g of x naught is not 0, f of x divided by g of x is the limit of f divided by the limit of g, which is f of x naught divided by g of x naught, because f and g are each continuous, which is exactly the quotient function evaluated at x naught. So therefore the sum, product, and quotient are continuous, as they're equal to their function evaluation and the limit as x approaches x naught. So let's take a look at an example. Let's see how could we use this. And by the way, just an idea of how we should think about results like this. We really should think of theorems like this as a shortcut. Not only a shortcut, but even a license and encouragement to take shortcuts. Typically, if you want to show that a function is continuous, right, we have to show for any epsilon there exists a delta such that the rest. But now, if we can show that a function is built from other continuous functions by either addition, multiplication, or division, well, just by that reasoning, we can show that our function is also continuous. So let's consider the case f of x equals x to the k. Let's show that this is continuous everywhere. And since we want to show that it's true for arbitrary natural number k, well, let's do that by induction. First, we need to show that f1 of x equals x, that is, x to the 1, is continuous. But hopefully that's clear, right? Because if x minus x naught is less than epsilon, well, f of x minus f of x naught is x minus x naught, which by assumption is less than epsilon. And since x naught was arbitrary, f of x is continuous everywhere. Now for the induction step. Suppose that f of x equals x to the k minus 1 is continuous. Then f of x equals x to the k is the same as x to the k minus 1 times x. Well, x to the k minus 1 we're assuming to be continuous, and we've already shown that x is continuous. Since x to the k is a product of two continuous functions, it itself is continuous. We can actually extend that idea to say that polynomials must be continuous everywhere. Why is that? Well, constant functions are clearly continuous. In fact, you could show that so long as x minus x naught is less than, well, any number, f of x minus f of x naught is equal to 0 if f is a constant. Not only can you do it, you will. It's in your homework. So since a constant function is continuous and x to the k is continuous, well then c times x to the k is also continuous. And if I have a sum of a bunch of coefficients times x to different powers, that's continuous. So all polynomials are continuous everywhere. But by the way, a quick note, when we say that a function is continuous on a set in its domain, we mean it's continuous for every element in the set. Well, that's it. Bit of a short lecture today. Hopefully there'll be more next time. That's all for today.